As always, can you see and hear me? I can verify that you can see me, but can you hear me as well? Yes, perfect. Can someone say something?
Yes, we can hear and see you,
Mhm.
and I suppose you can hear us.
Yes, this works out as well. Thank you very much. So let's start for today. Um, yeah, today, 2 hours earlier than usual. This applies only to this date and time. So next week we are meeting at 9:45. What we're doing today is basically picking up from where we left off the last time. The main topic was finishing the Linux crash course, which we successfully did. And the next bigger topic is memory management. And we didn't talk much about memory management, but we did a little peek into the topic. And we introduced the first concept of caching, how caching works and how it does speed up faster and slower storage levels using a small amount of faster but more expensive memory, and using this faster memory for data that is accessed in a high frequency. And then we talked a little bit at the end about address spaces. Address spaces being the core concept of memory management, how memory is managed in modern operating system, and it's the same in Windows, in macOS, and in Linux, and all FreeBSD or other smaller operating systems. Because the issue with granting processes direct access to physical memory is twofold. First, if a process has direct access to memory, a process can corrupt other processes. So it can overwrite memory locations where the operating system kernel lies, for example, or other processes lie. So this is crucial for the stability of a system, such that one process cannot have a severe impact on another process, in a sense that one process can crash the other process. The second one was that if a process has direct access to physical memory, it's also possible to dump the contents of other processes, meaning this is an IT security issue where one process can read the memory contents of another process, and therefore gain access to secrets such as passwords that are stored in RAM, or security tokens that are used for online banking or other security sensitive tasks. So we cannot allow processes to compromise other processes and dump the memory contents of other processes as well. So what do we do? And the idea is to introduce a concept such as address spaces, meaning an address space is a emulation/simulation such that the operating system simulates a free memory space for every process individually. So this is the idea. Every process gets a range of virtual addresses, and these addresses are used exclusively in an isolated manner by each process. So every process gets its address space. It's distinct, so it's isolated from all other address spaces, and they start and end at the same address, meaning that the range of addresses is the same for each process. So every process gets an address space, and this address space starts at an address number of 0, and it ends at a very high address number. So typically when we have 64-bit operating systems, the upper limit of an address space is the highest number that we can express in a 64-bit system. And this is 2 to the power of 64, which is a really big number that I cannot express in words. So it's very, very big. So address spaces start at 0 and end at 2 to the power of 64 and are separated by each other. And the mapping between these virtual addresses that are part of an address space, so the simulation a process sees, and the mapping of these virtual addresses to actual physical memory locations, because we still have a limited physical memory. This is done by the operating system. This is supported by hardware, as we will see today. And this is like the core of memory management, how to do this properly in order to make it efficient. Because when we're talking about memory access, performance, like the time we require to perform a access to a memory location, is crucial to the overall performance of a system. And each step, because it's so low on like the level we are talking, so every millisecond, microsecond, even nanosecond that we add to the access time of a memory access will hit performance of the overall system significantly. So this virtual address concept with address spaces need to be very performant, such that it does not take too much of a hit to the overall performance of the whole system. But what we get in return is a system where we, for example, can have two processes or even two instances of the same program. So two processes of the same program that can use addresses in their own address space. So imagine that you open the browser for 2 times, Firefox open 2 times, and all the addresses that are encoded in the instructions of these programs. So in this example, it's address 28 hex. These are hard-coded in the instructions of the program. But this is not an issue anymore, because address 28 hex in one program has or works in its own address space and is mapped to physical locations by the operating system, meaning that 28 hex in one program is an entirely different physical memory location as address 28 hex in another program. So by this mapping virtual addresses to physical addresses by the operating system, we achieve this isolation requirement that we have, that one program should not or must not interfere with another program. So the first question that arises is, well, how can we do this technically? And the most naive version to do so is relocation, meaning that we translate the address space of a process to a specific segment of physical memory. So, I mean, I said earlier that an address space is pretty large. Like it starts from 0 and it ends by 2 to the power of 64. But processes do not need as much memory. So let's assume that the address space of a process is as small as possible. So the minimum amount a process requires to run in memory. So this is our baseline assumption for relocation. Relocation, we take a look at a special variant of relocation. There are two ways of do relocation: static relocation and dynamic relocation. And as dynamic relocation is the more sophisticated one of these two approaches, we will talk about dynamic relocations. And this involves two hardware registers. It's base and limit. And base and limit constitute the boundaries in physical memory where a process address space might lie. So base is the lower limit, and limit is like the upper limit or upper boundary. And together they form like a consecutive segment of physical memory. And if you remember the introduction of operating systems, there we talked about concepts such as time sharing and also multi-programming. And in multi-programming, we have exact this scenario where we have multiple programs loaded into memory. And for example, the first program is at the bottom of the physical memory when we count the addresses from low to high address. So program 1 is at the bottom, and then we stack the next program on top of program 1. So program 2 is on top of program 1, and program 3 would then be on top of program 2, and so on and so forth. So this is the idea. But still, when we're talking about relocation, and the argument that we had before, like that a program consists of a sequence of instructions, and these instructions address main memory, address RAM, by using addresses. These addresses are hard-coded in the instructions. So when we use a concept like relocation, the question is, how does the operating system need to modify these hard-coded instructions in order to shift the segment to another space in physical memory? And for that, base and limit, mainly the value of the base register, is used. Because whenever a process references memory, so whenever an instruction is executed that accesses memory, the operating system, or basically the CPU, because it needs to happen very fast, so it's supported by hardware, the CPU adds the base value to this address, and this way shifts the address that is hard programmed in the instructions by a certain amount up. So it starts at 0, and when the base value is, for example, 6000 hex, then the address 5 hex is relocated to 6005 hex, because we add the base value to all addresses that we find in an instruction. As this is dynamic relocation, so this is a general rule, dynamic things that are declared dynamic happen at runtime. So this, like, recalculating of addresses happens at runtime, like during the time the process runs, as opposed to static relocation, where this translation is done not at runtime, but at loading time. So the time when the program loads from secondary memory, so from hard drives, into RAM, then this recalculation of addresses happen. But this would be static relocation. We are focusing on dynamic relocation, where we do this at runtime using these two hardware registers, base and limit. Yeah, and if a process tries to access a physical, or tries to access a location that is above the limit, then a fault is generated, and the operating system will handle this. Whereas handle this is, in fact, it will terminate the process, because the process did a memory access that the process is not allowed to do, which in technical terms is called a segmentation fault. And the process is then terminated ungracefully. So we also say the process is killed. So killing a process is an actual technical term. So process is killed if it tries to access a memory location that it is not supposed to access. Yeah, what we see here is an illustration of dynamic relocation. So consider these two processes. We have process A and process B, and we have the register values here. So process A, which is in blue background, starts at a base of 0 hex, and it ends at 3 FFC hex. Again, don't be afraid of these hexadecimal numbers. These are numbers, and we can do whatever we want to do with these numbers, but they are just expressed in a more compact form, which is the base of 16, which are hexadecimal numbers. But these are like still numbers. And in process B, which has a green background, we have a base of 4000 and a limit of 7FF8. And if we map this into physical memory, the operating system will say, well, we stack these processes up, meaning that process A here in physical memory on the right-hand side is at the bottom, and on top of process A, we stack process B, and we put process B then on top of it. And regarding addresses that are in instructions, so we have this example here at this JE instruction, which is jump instruction, you don't need to know the specifics of this. But what you need to know is, well, we have like hard-coded addresses in the instructions of a process. So what do we do with this? So we load the memory, we load the instructions into physical memory, and we do not change them during loading. And when this instruction is then executed, so this JE0 hex, then the CPU adds the base value. The base value would be 4000. So this address here is translated from 0 hex to 4000 hex, which is the bottom of the address space of process C. So you see this in color encoding. This is the first address of this address space starting at 4000 hex. And the same for the blue one, right? So we have a jump instruction that jumps to the instruction that is found at 8 hex. 8 hex would be this add instruction. And as the base is 0, it does not change because adding 0 does not change the value of a number. But this is, I mean, this is how dynamic relocation works. So whenever we access memory, we reference memory, we add the base value of a process. And what we achieve is basically a shift of the segment of the memory address, like this consecutive segment of memory, and we shift it to higher addresses by adding this base value to all memory reference. Okay, this would be the method of dynamic memory location. But things happen when we do dynamic memory location, and one like drawback or one situation that we need to consider is memory overload. So this is all fine, right? So this works out with a physical memory that is big enough, and it works out fine with a small amount of processes. But as it turns out, we run a lot of processes in our operating systems. A lot of processes. Let me just count how many processes that I am running currently. So I have my streaming setup running right now. Oh, the terminal isn't shown. Can I enable the terminal? Yes, now you see the terminal. And in order to see how many processes you are running, you can execute the ps command in Linux. You get the most out of the ps command. This is something that you can remember if you enable the options AUX, because then you see these are all the processes that are running on your machine. So for example, I'm running Chrome because I'm in the Zoom chat with Chrome. I'm using, here you see the OBS process. So I use OBS to like record the camera and do all the video mix-ins. My terminal is called console. You see the process there, and so on and so forth. So question would be, how can I count how many processes are running? Well, I pipe it into WC and count the lines. And right now I'm running, oh, you don't see it. I'm running 516 processes, which is a lot. So 516 processes that need to fit into memory. Fortunately, I do have a lot of memory installed on my system. So bringing HTOP up, you see that my laptop is under load because Google Chrome requires a lot of CPU time, and then I have OBS Studio, the recording software that I'm using, that requires a lot of CPU time. But memory-wise, I'm fine-ish. So right now I'm using 11.6 gigabyte out of my, well, it shows 27 gigabytes, but I have 32 gigabytes installed on my laptop. So let's say roughly a third of, 40% of my main memory is occupied right now. But what if I start more and more processes? So we need to have a concept for this situation, and the concept is swapping. So swapping is a strategy that deals with memory overload. So what do we do when physical memory is full? And this happens, I mean, you're artificial intelligence students. So this happens in your use cases all the time, because when you train large machine learning models, then RAM will be full all the time. So what do we do in this case? Well, we can swap. The idea is that we select processes, so 1 or 2 out of my 516 that are running on the system, and we take the address space of a process, and we write the content of an address space to secondary storage, like to my hard drive, to free up the main memory for other processes. So basically, I have a list of my 500 processes, and I need to select some processes that I throw out of main memory in order to make space. And in an ideal world, I select the processes that do not, or are like not active in a sense, that are actively running processes, but are processes that run in the background. So our idle processes do not need much resources. And if I select those processes, I can like swap them out. This is the technical term for that. Swapping out meaning I write the address space of a process to disk and removing it from memory, creating space for processes to be swapped in, like reading an address space from disk and loading it into memory. Swapping in happens when we start a new process, because process starting meaning that we load the program from our hard drive, loading it into memory, and then start the machine instruction cycle that we discussed some weeks ago, where the control unit of the CPU fetches the instructions of a program from memory and then pushes these instructions to the ALU, to the arithmetic logical unit for execution. And this happens when we load a new program, create a process from a program, then we are swapping in an address space from disk and loading it to memory. And if memory is full, we swap out processes like writing the address space to disk and removing it from memory. And this happens when we have a high load on our memory. So we are close to memory overloading. Swapping in and swapping out happens a lot. And the result being that your physical, like the physical memory, looks like Swiss cheese. It has a lot of holes in it because we swap out different sizes of address spaces, and we also swap in different sizes of address spaces as well. And if we do this over a long period of time, we get holes in our physical memory. This is something that we need to think about it. But the other thing that we need to think about it is, well, how do we select a process that we throw out from main memory? And if we have a memory and it is full of holes, when we swap in a process, a question arises, well, in which exact hole do we place this new address space that we load from disk? And these are two very non-trivial and complex questions. And algorithms for answering these questions are one of the main topics in memory management and will be one of the main topics of our lecture today. So let's start easy. Well, the most challenging task is selecting processes to swap out. But you can make your life easy by just picking a simple algorithm for that. FIFO, first in, first out, is one of these algorithms that are rather on the simpler side, but this does not mean that FIFO is bad. FIFO might be good in some use cases, but we will see in an hour or two that we have alternatives to FIFO that select the processes to swap out a little bit better than FIFO. But as I said, we start with an easy example. Let's do FIFO. FIFO meaning first in, first out. It's like a queue at the market. So if you enter the queue before checking out, like in Aldi in Germany, you have to wait until the checkout process is finished for all customers that entered the queue before you. And this is first in, first out. In terms of processes, this means that we choose the process that has been in memory the longest. So we keep track, when do we swap in processes, and we simply select the process that had the longest time in memory and throw this out. For swapping in, we have 4 options that are used in practice. The first one is first fit. So this determines, well, we have a memory that is full of holes, and we need to determine the hole where we swap in, like load in a new process into memory. First fit does it in a way where it starts at the lowest address, bottom up. So it starts at address 0 hex and it ends at like the upper limit of the address space. And it scans the memory for holes and it stops at the first suitable hole. So for example, if we have a process A and the process A requires 10 megabytes of main memory to run, then first fit starts at address 0, goes up the address space, and if it finds a consecutive segment of 10 megabytes free memory in the physical, or like, yeah, it's in the physical, in the physical memory. If we find a consecutive segment of 10 megabytes in physical memory, we place the process there and use, for example, dynamic relocation in order to translate the addresses on the fly during runtime. First fit runs bottom up, stops at the first hole. Next fit is a variant of first fit. So it starts bottom up, so it scans bottom up and stops at the first suitable hole, but the scan begins where we previously left off. So if we do it like multiple times in a consecutive manner, next fit obviously starts at bottom up, but it remembers the location where the previous run stopped, so where the previous suitable hole was located. And this is the starting point for the next iteration, for the next invocation of next fit. So we restart where we left off before, a variation of first fit. The benefit of these two algorithms is that they are pretty fast, because as opposed to best fit, which does not stop at the first suitable hole, but scans the whole memory, so all the addresses that we have in memory, to find like the best hole. And the best hole in our context is the smallest suitable hole. So best is measured in how much memory is left over if we place the process in this exact hole. We do this for the entire memory in order to find the smallest suitable hole. And you see the difference between first fit and best fit there. Best fit might have a better result if we aim for making like the holes as small as possible in order to achieve a high degree of utilization of our memory. So this can be achieved with best fit, but on the other hand, first fit is faster because it does not need to scan the whole memory. It just needs to scan until a first suitable hole is found. And if the first suitable hole is at lower addresses, then first fit terminates way faster than best fit. There's another strategy, it's worst fit. Worst fit sounds strange, but in fact, worst fit is not bad at all. So it also scans the entire memory, but the goal in worst fit is not to find the smallest suitable hole, but the largest suitable hole. Because it turns out that if we use the largest suitable hole, we have a larger consecutive segment that is left over if we place a small process in a larger hole. Then we have a somehow not as large as before, but a bigger hole that remains for other processes to be filled in. And please do not like rate these algorithms where you say, well, best fit is the best algorithm for swap-in and worst fit is the worst algorithm for swap-ins. This does not apply, because I know applications where best fit and next fit are employed, but I also know use cases where, for example, worst fit is used. So if you know Python programming, for example, the free space management in the Python programming language is based on worst fit. I will not go into detail, but this is an application in the most used and most popular programming language that we have currently. Worst fit is applied there. If you ask the question, well, why worst fit? People do not know as well, but they took these 4 alternatives for swapping in processes into memory, and they just did experiments. So they tried these 4 things out, and it turned out that for Python and the parameters and the use case of Python free space management, it turns out that worst fit delivers the best result. So here, just like a side note, do not rank these algorithms in this is the best, this is the worst. They might deliver the best results in different use cases. Let's do an example. So in this diagram, you see we have 8 times where we load in, like where we swap in and swap out processes in order to demonstrate what happens with memory management over time. So you read this diagram from left to right, where we have 8 dedicated times where we take a look at memory. And we have 4 processes, A, B, C, and D, and we have, let's say, a small physical memory because it needs to fit on my slide. So please consider that in practice, obviously we can host more process in memory. So you saw before I'm running 500 processes and I have a 40% utilization of my main memory. But in this case, it's small. It's a minimal example. And let's say we do FIFO. So when we need to swap out a process, we select the oldest one. And let's say we do first fit. So we scan the memory from bottom to top in order to find a hole that fits our process. And the size of the process is illustrated by the height of the rectangle that you see here. And let's say we want to swap in, or let's say we want to execute processes A, B, C, and D in a consecutive order. And then we do it again. So we execute A, B, C, D, A, B, C, D, A, B, C, D, and so on and so forth. So if you take a look at time t0, main memory is empty. At the bottom, we have the operating system, because the operating system obviously is a program and also requires main memory to run. So we need to reserve some main memory for the operating system, and then we have program or process A that's loaded. According to first fit, we start at the bottom. We take a look at the first hole that fits the process and locate the process there. So process A is located there. Process B, well, the hole is, or can I highlight this? Yeah, there was an update in my presenting. So the hole for process B would be this, right? So this is the first hole that we find for B, and we place B in there. If we want to load C, this would be the hole that we find according to first fit. Well, there is only one hole in this minimal example, but still, this would be then the hole, and we place process C in there. So next we want to load D. Here, pointer, oh, did it work? Remove that real quick. Now I have my pointer back. So now take a look at the process D. D is a little bit bigger than A. I hope you see this. It's not much, but D is a little bit bigger than A. But what you can see is D cannot fit into the hole there, right? So we found a hole according to first fit. This would be the hole where we can place processes. But process D does not fit into the hole. So here we are at the situation of memory overload. So we need to swap out. We need to swap out a process. So what we do first is, let me draw a line there. Here. So the process that we select for throwing out of main memory, it's based on FIFO. FIFO meaning the longest process is removed. The longest process in the system of A, B, and C is A, so we remove A. The thing is now, in time index 3, the thing is we have a hole at the top, we have a hole at the bottom, because you need to think that B is still in main memory. We just removed A, but we still cannot fit in D because it does not fit at the bottom, because D is slightly bigger than A. So it does not fit in the hole that was created by swapping out A. And it does not fit in the hole at the top because it's too small. In this situation, we need to select another process to swap out in order to make the or in order to make space in main memory. So what is left over is B and C. B is a longer time in memory than C, so we select B for swapping it out. And therefore, we create this hole, this one. And D fits into this hole, so we place D there. And next, so we have loaded A, B, C, D, and we swapped out A and B. Next we do, or let's say we want to have A in memory as well. Here we have another situation. Like we have two holes in our memory, if you take a look at T4. And if we want to swap in A, we need to find a hole where A fits into it, right? And if we do a sneak peek on T7, you see what kind of effects happen if we swap in and swap out processes this way. Because we see that we can, in fact, host all three processes, A, B, and C, in the physical memory. So in total, they fit into physical memory, but we cannot load A in this situation T4 because we do not have a consecutive segment of memory where we can place A. We have a small hole here in the middle, and we have a small hole at the top. So although we would have enough space to host A in physical memory, we need to swap out C because we do not have a consecutive segment of memory that we have available. So we need to swap out C. C is removed, so we have place for A, fine. And then we want to load C again. C has enough space at the hole at the top and fits in there. So what I want to stress out here is an effect that we call external fragmentation. External fragmentation in the sense that although we would have enough free memory in total, there is no consecutive memory segment available, and we need to swap out this process C and swap it in the time between T4 and T7. This is what we call external fragmentation. And in theory, this swapping out and swapping in again is not required because the physical memory should be able to host all three processes at the same time. And remember, so if we remember this this pyramid that we had in a couple of weeks ago, swapping out means that this process is written on disk, and the access times between memory and disk it's huge. It's huge. It's factor 100,000 a million. It's factor a lot. So whenever we swap out and swap in a process again, like here, we swap out C and swap it in again. This takes up a tremendous, huge amount of performance compared to just direct memory accesses. And this is pure poison for operating system performance. There is no bigger poison than swapping in and swapping out for an operating system. I'm bringing up my terminal real quick. Oh, it still runs. So whenever you have a situation where you load too many processes into your operating system, that you have, or that you go to the upper limit of your installed physical memory, then swapping happens. Swapping happens at my operating system as well, but luckily I have some memory left. But if I would have 8 gigabytes of memory, for example, then the operating system would start swapping processes in and out, and I would not be able to do an online lecture here because my system would be slower by a factor 1,000, 10,000, or even slower, because memory access is poisoned by external fragmentation, which means we have disk access in order to run all these processes. So take this into consideration. Let's train this before we go further. There's a task swapping on iLearn. Let me switch over to that. Swapping. It's a nice task because yeah. Let's take a look at this task. So let's assume we have a physical memory. This physical memory has holes in it. In ascending order, we have holes A to holes H, and what you see next to the hole definition is the size of the hole. So the first hole that we find in memory is 10 megabytes, the second one is 4, the third one is 20, and so on. And then we need to load processes into memory. Let's say over time we load process A, then we load process B, then we load process C. And the question is, in this scenario, what happens to memory to first fit? What happens to memory with best fit? And then as homework, next fit and first fit. So let's do first fit and best fit. And your task is to assign each process to a hole where the process will be loaded according to the first fit strategy, and the same for the best fit strategy. You have 15 minutes of time for that. This is an old exam question. So this is, again, in the phrasing and in the scope and in the amount. This is what you need, or what you can expect in an exam. And I would give for first fit and for best fit, I guess in total I would give you 6 minutes. But as you can take a look at lecture slides, you can discuss in groups, because we do breakout rooms again. Then you get a little bit more time, but that you get like a feeling on how these practice exercises that we do in lectures reflect to exam questions. So let me create some rooms. 4 to 5 participants equals 8 rooms. 15 minutes, and the rooms are created right now. Well, we start from bottom and go to the top. Does process 2, which is 10 megabyte, fit into hole A? Yes. So process 2 goes into hole A. Oh, I made a mistake before. Process 1 does not go into hole A. Process 1 goes into hole, what was it, C. And then we have process 3 the same method applies. Process C is 9 megabytes. Does it fit into A? If A wasn't occupied with process 2, then it would fit into it. But as process 2 is assigned to process A, there is no hole left. It does not fit into B. It does also not fit into the leftovers of C, because the size of C shrank to 8 megabytes because it hosts process A. What's left over are 8 megabyte. Process 3 is 9 megabytes, so it does not fit into hole C. So we need to place it in hole D. Does the order of the processes matter? Absolutely does it matter, because of the scenario that we just described. And it is also, like stated in the question, so the following processes need to be loaded into memory one after another. So process 2 after 1, process 3 after 2. So the order does absolutely matter, because it makes a difference if you load process 2 before process 3, because if we do it otherwise, so we change the order, process 3 before process 2, then process 3 would be in hole A instead of 2. So order matters here. Let's take a look at best fit. So this is my allocation for best fit. Best fit meaning that we scan the whole memory. So we do not start at the bottom to top and stop at the first suitable hole. We take a look at all the holes in memory and place the processes such that the leftovers are minimal. Right? So for process A, we have 12 megabytes. We place it into hole G because hole G has 12 megabytes of space. So we have 0 bytes of leftovers. This is the smallest hole we can fit the process in. So we place A to G. We place 2 to A because 10 megabytes and 10 megabytes. And we place process 3 to F, because here again, it's the smallest hole that can accommodate process 3. As homework, we do next fit, like a variation of first fit, and we do worst fit as a variation of best fit, in order to have a starting point for the next lecture, as well as you having the ability to train, or the possibility to train these algorithms at home. Are there any questions? Okay, then we proceed with external fragmentation. We talked about the concept before. Again, to refresh your memory, what happens if we constantly swap out and swap in? Holes are created, holes are filled, but memory will be divided across the segment of physical memory, the whole range of physical memory, and we will have sometimes smaller, sometimes bigger holes in main memory. And if we want to allocate like a large consecutive memory segment, then we have the challenge to find the correct hole. And sometimes we do not find a hole that is big enough for like consecutive memory or contiguous memory segments to fit into. Here we have the situation. In time 4, we would have free memory in total to accommodate A, but the total amount of memory is split into 2 holes, so we cannot fit A into either of these 2 holes. This is called external fragmentation. And it gets worse if time, or not if, it gets worse when time is progressing. It's the biggest poison that we can have. And like ideas that we do defragmentation of memory, and the technical term would be their memory compaction, where you relocate all the processes to the bottom, such that you eliminate holes. This is basically a good idea. And this kind of compaction, defragmentation is also done in old hard drives. So the idea is not bad, but the thing is that this technique will take too much time if we do it in memory. And we have just a simple calculation there. So if you take a 16 gigabyte machine and we can copy a byte in a nanosecond, which is not far off practice. What did we calculate? One memory access is around 200 picoseconds in the latest generation. So copying 8 bytes in 8 nanoseconds is not something that's super far off. And then if you put in the numbers and calculate the time that you need for memory compaction of a 16 gigabytes machine, it would take 16 seconds to compact all of the memory, to relocate all the processes such that you eliminate all the small holes and create a one big hole at the end of the memory space. And 16 seconds is a long time, because what you need to do is stop the world. So during the time where you do the memory compaction, no processes is allowed to either read or write to memory, because you are doing the relocation just right now during the memory compaction time frame. And if you remember, oh no, not remember, if you think about the scenario where your PC freezes for 16 seconds, then this would be something that you would not accept at all, right? So for every couple of minutes, you have a freeze of 16 seconds, no one would accept that. So technique is good, but it's impractical because the user would not accept this. So to sum address spaces up, so we have still challenges with the idea of address spaces. The most severe challenge is external fragmentation. The biggest poison, leads to substantial performance degradation. We did not consider scenarios where we have programs that are larger than main memory. So we are lucky that we live in an age where we should have enough memory in a computer to fit most of the programs, but still, use cases in artificial intelligence where you have large data sets that you need to process, and you need to do number crunching and computations in memory. So you have use cases and programs that do not fit into main memory, even if your main memory is like 3 terabytes. So I've seen these use cases before, training large machine learning models, and then the data set is way bigger than the amount of main memory that you have available in your machine. All active processes must fit into memory. Otherwise, we swap in and out. Active in a sense that it is a process that currently runs. So it's not idle, it's not suspended, it's not a background task. It's a task where user interaction is required. So for example, my slideshow here, or my recording software, or my terminal, which requires input and output. Input being like keystrokes that I put into the keyboard, or mouse movements, mouse clicks, and so on. The browser would be an active process. And all active processes must fit into memory, because otherwise we swap it out, and the likelihood of the process being used in the near future is high. So the likelihood of this process to be swapped in is high. So we have a constant swap in, swap out, swap in, swap out, swap in, swap out. And this is a substantial performance hit as well. And what we did not consider is dynamic memory allocation. So what if a process needs memory like during execution? So far, we considered a process, or we considered memory that a process requires, just as the memory to hold the instructions and to hold the data for the instructions, so the operands of the instructions. But most programs require memory on the way. So Consider Photoshop, for example, or consider a word processing program like Microsoft Word or Microsoft Excel. Microsoft Excel, if you start it, it does not require a lot of memory. But once you load a spreadsheet with 20,000 rows and 5,000 columns, then Excel requires a substantial amount of memory to hold this like bigger spreadsheet. So during the runtime of Excel, it requires memory depending on which spreadsheet the user opens. This is dynamic memory allocation, like memory allocation that happens during the execution of a process. And we did not address this so far in our model. But to wrap the idea of address spaces up, it's a good idea. It is used and it is employed today. And but we need some more methodology, some more techniques to make this idea of address spaces work, because the alternative is unacceptable. The alternative would be that we allow processes physical access to memory, and this would break all security concepts and all stability concepts that we have. This would not work out. We would not have the computers that we have right now if processes would have access to physical. So I need to fix the camera real quick. So my camera, it's powered by AI. So it understands gestures. And my camera now follows me. So if I, there you see it. So it follows my head. And if you see, it follows my head to an extent that it goes over the green screen that is in the back, right? So you see this is the room behind me. So I need to turn off the following feature, and I do this by making this gesture. So following is now off. Okay, camera is fixed again. And I will place it a little bit such that you have enough space. Okay, perfect. Now my camera is fixed. So when I'm like gesticulating, sometimes I trigger this kind of AI-powered gestures to turn features on and off. Okay, next we talk about virtual memory. Virtual memory picks up on the idea of address spaces. And address spacing being virtual range addresses that processes can use. Every process has an individual, isolated, separate address space. So, virtual memory. The concept of virtual memory is that you extend these address spaces by a large amount. And I said this before. So this large amount is from 0 to 2 to the power of 64. And you are able to address memory because obviously the number of addresses in this address range is way higher than you have physically installed in your physical memory. So this is like, it's even above the exabyte range. And you can access memory which does not lie in physical main memory, but it lies on secondary memory, so on the hard drive. And you can address memory locations that are located on a hard drive the same way as it were located in main memory. So basically what this means is you extend the concept of main memory by some amount of disk memory as well. But you leave the allocation scheme the same, such that processes can access memory which is physically stored on a hard drive the same way as if the data in the memory location would be in main memory. And this is the concept of virtual memory. So processes receive a full virtual address space and address memory locations, or an address memory locations, and the memory, the physical target can either be secondary memory and main memory. And in order for this to work out properly, we group main memory into what we call pages, which have a fixed size. So who remembers, please write in chat, how much information I can store on one memory location? Answers in chat, please. Eight bits is correct because we have an byte addressable main memory. So one memory location holds 8 bits. And we group 4 kilobytes of memory, typically, in pages. So we group 4,096 memory locations together, and this would be a page. Right? So 1 byte, 1 location, 1 page, 4 kilobytes of main memory, resulting in 4,069 memory locations, memory addresses. Be aware, kilobytes is a size, so we have it in binary prefixes. Binary prefixes means it's, 1 kilobyte is 2 to the power of 10, and 4 kilobyte would be then 2 to the power of 12. Right? Yes, 2 to the power of 12. Let me double check. 2 to the power of 12. Yeah, 2 to the power of 12 is 4,069. So 4,069 memory locations, 1 page. So as we have virtual memory addresses in our address space, we call 4 kilobytes of virtual memory, the group of 4 kilobytes of virtual memory page, and the equivalent in physical memory, page frames, such that one, like a frame is frame, such that you can put a page in virtual memory into a page frame in physical memory, because you need to map addresses in virtual memory to physical memory with the idea of virtual memory and address spaces. So typically, if you have 4 kilobyte pages, you also have 4 kilobyte page frames because they need to fit together. Technically, if you are not the brightest person to say that, you could configure pages and page frames with a different size. So you can have larger pages and smaller frames, but then you need more frames to fit a larger page, which does not make sense. Or the other way around. So you can have larger frames than you have pages, but then you can just put one page into a frame and you would waste memory. So this is not a good idea. So this is in a one-to-one relationship where you have one page in virtual memory and you fit it into one frame in physical memory. Right? And these pages in virtual memory are mapped to either frames or the disk. Let's see this example here. So in this diagram, it's a minimal example. You need to scale it up to reach like real world examples. But here we have a physical memory of 32 kilobytes, so a small physical memory. Right? And as we have a page and a frame size of 4 kilobytes, we have 8 frames in total. And as we are computer scientists, we start counting at 0. So we have page frame 0, which ranges the addresses from 0 to 4K. Be aware this K, it's kilobytes, it's expressed as binary prefixes. So this ranges from 0 to 4,095, because we start counting at 0 the last address on page frame 0 is 4095, and the first frame, the first address in physical memory on page frame 1 would be then 4096, and 4096 being 2 to the power of 12. And you see we have a bigger virtual address space. So we create the simulation of a big virtual address space for each process, and we call like the groupings, the elements, the segments of virtual address space pages, 4 kilobytes in size, and the operating system does a mapping. So let me highlight again. So page 0 ranges from 0 to 4 kilobyte, minus 1 because we start counting at 0. And the mapping here, so hopefully I get this right. So the mapping would be this. So we map page 0 from the virtual address space to page frame 2 in physical memory, the physical memory space. And if we take a look, for example, at page 10, page 10 does not correspond to physical memory. Page 10 in the virtual address space lies on disk. So for a process only has the view, the perspective of virtual address space. A process does not know that this page 10 is on disk. The operating system knows, yes, because the operating system does the mapping. But the process does not know which pages are in physical memory and in disk. And here we have the situation where, for example, this process has 12 pages of 12 pages. So with this concept of introducing pages and having pages mapped to either frames in physical memory or disk, we can run processes that require a higher amount of memory that is physically available in the machine. Also, you see the mapping is, it's not arbitrary, so there is in fact a strategy how to do this mapping. And you also see that external fragmentation is eliminated as well, because we do not need a consecutive or continuous segment of memory, because we can do the mapping on like 4 kilobytes of chunks, meaning that we can have a process running in its virtual address space, and this address space uses different locations of physical memory and does not need a continuous amount of memory here. So we strike multiple birds with one stone. We can have processes that require a higher amount of main memory, having pages pointing to additional space that we have on disk, and we eliminate external fragmentation because we can place a single process into non-contiguous physical memory addresses. And this is a benefit. Question, virtual address marked with X represent? Well, X means that this is unallocated address. So the address space ranges from 0 to 64K, which is double the physical memory, and the process like requires 12 pages to run, and the top 4 pages are unallocated addresses that do not need to be mapped. Okay. Yeah, I have my pointer again. So this is the idea of virtual address spaces. And this is the concept that is implemented in all operating systems. So this runs in Linux, this runs in Windows, this runs on Macs, and this runs basically on any modern operating system. So this idea. Now we need to think about multiple things. The first thing is the idea is good, but I always tell you that it is crucial to be very high performant when it comes to memory access, because this is the most crucial thing that we have in a computer. Like memory access, if memory access is slow, it slows your whole computer down. Now we have a mapping between virtual addresses and physical addresses. How can this be fast? Because I said, well, the operating system does the mapping. And the operating system is a software. So in order to perform the mapping, the operating system requires some time to do so, right? And if we would implement this in software, we would need, let's say, 20 cycles. But a memory accesses one CPU cycle, not 20. We cannot afford to have this mapping being in software consume instructions. So this mapping needs to happen like during the cycle of one memory access. And in order to do so, in order to be as fast as possible, CPUs have another part, like next to the CU, next to the ALU, next to the registers. CPUs have a component that's called the memory management unit. And this is a part of the CPU that translates virtual addresses into physical addresses. So the CPU needs to support this idea of virtual memory. And it does it since like the 80s. And the MMU does exactly this mapping in like electrical circuits such that it happens like in an instant and can be done as part of accessing memory. Now let's take a look how this MMU works. So it's an intermediary between the basically between the control unit and the main memory, because the MMU is part of the CPU. So the control unit decides, well, we need to fetch this address because this is the next instruction that we want to execute. In between, basically between the bus and the CPU, we have a component memory management unit. And the CU emits the virtual address that it wants to load. The MMU does the mapping and puts onto the bus a request for the physical address. So the translation happens in the CPU. And then the physical address is requested from the memory module. Here, again, as an application for caching, we have a cache to speed these things up. And without that cache, again, these caches have a tremendous benefit in this kind of speed ups. The cache in this scenario is a translation look-aside buffer. So the MMU diagram, I guess, in the next slide. Yes. So when the control unit wants to have a certain memory address, as a man in the middle, the MMU gets the virtual address that the CU wants to load, takes a look in the translation look-aside buffer, which is a cache to the MMU. And if the physical address and the content of this RAM is already in the translation look-aside buffer, we take the information right of the translation look-aside buffer and everything is fine. If the information is not found in the translation look-aside buffer, we access main memory through the bus. So we do the translation, and we emit the physical address on the bus, and the memory module is then read, and we get the content through the bus to the MMU. Example. So let's assume that we want to have the address 8196, which is 2004 hexadecimal. So 8196 decimal is 2004 hex. So these two numbers match together, but with a different basis. So this is an actual instruction. So move EAX 2004 hex means what happens, this is an instruction. and so an actual instruction on Intel and AMD CPUs. It loads the content of the memory location 2004 into register AEX. So the content of this address is loaded into the register, which is called EAX. So what happens like inside is the CU sees this instruction and sees, well, we need to fetch the content of the address 2004 hex, which is 8169 decimal, to the MMU. I put on decimal numbers because it's easier for us humans to understand this. So let's do it in decimal. So the CU passes the address 8169 to the MMU. The MMU identifies page 2. So the MMU takes a look at the configured mapping. So at first we need to identify, well, in which page is the address 8192. Maybe I set up my whiteboard here. Wait a second. So do you see this when I write hello class? Yes, you can see this. Perfect. So page 0. We know that page 0 ranges from 0 to 4 kilobyte. 4 kilobyte minus 1, because the last address is 4 kilobyte minus 1, because we start counting at 0. So this is the last address in decimal for page 0. Page 1 starts at 4 kilobyte, which is the first address is then 4096, and it ranges to 8192, right? Because this is 8 times 1024. 1024 is 10 to the power is 2 to the power of 10. This times 2 would be 2048. This times 2 would be 4096. This times 2 would be 8192. So this in total is 2 to the power of 13. So this is a binary prefixed number, right? And page 2 would be then actually made a mistake, because it's minus 1. We start counting at 0. So the first page is 8192, and this would be then 12 times 1024. I need to have, let me real quick, using the calculator there. Oh, don't I have a calculator? That was too fast. Wait a second, I have it right now. It's 12,288. But no, we need to subtract 1, because starting counting at 0. And so on and so forth. So this is how the addresses lie. So going back to our slide where we want to have 8196. So this is the address that we want to have, right? And we see this is in page 2. So we need to find the address, the virtual address, or the physical address for the virtual address 8196. So let's see, going back page 2. To which page frame does page 2 map? So hopefully I get this right. Yeah, it should be page 6. So you see here, page 2 maps to page 6. Page 6 ranges from 24K to 28K. So let's calculate the boundaries there. Going back to my iPad. So 20, what do we have? 20, oh boy, 24 to 28. 24 to 28K. So 24 times 1024 is how much? Putting it into my calculator, it's 24,576. The same for 28K, binary prefixes. So 28 times 1024 is 28,672. So the range of page 6, the page frame 6 is 24,576 to 28,172. So, not 72, 71. I'm making the mistake all over again. We start counting at 0. So this is the range of our page frame 6. So what does this mean? How can we map the 8,169 to page frame 6? So what you do is the following. So you know this address is in page 2. And if I draw this up, so this here we have bottom here. And let's make this a little bit bigger, right? So this is like page 2. And here at the bottom, we have 8,192, the address. And at the top, we have 12,287, right? And somewhere in between, the lower end of this address, right? So this is our 8,196. So what you do in this mapping is you calculate the distance of the address in the frame that you seek to the first address of the page period. So this is page 2. And we are interested in this difference, which is 8,192 minus the lower bound, which is 8,192. In the difference of the address that we want to translate to the lower bound is 4, right? So everyone on board. And next we want to map this page 4 to page 6. And page 6 is 24,576 on the lower bound and 28,627 on the upper bound. So what you need to do is you need to place the page. If page 2 is mapped to page frame 6, then you need to have the same position of the address in your page in the frame. So the position in the page frame, as the size is the same, needs to be equal. So this distance between the lower bound and the address that we want to map the physical address to needs to be the same. So this needs to be a distance or a gap of 4 addresses as well. So what you do is you add the distance to the lower bound of the page frame. So this would be then 24,576 plus 4. And this would be 24,580. So this is the address relative to the position, 24,580. In another color. What color do I pick? So this address, 8,196, is mapped to this address in physical memory. Because you map page 2 to frame 6, you have different address ranges in these pages, depending on where they lie. And you need to make sure that the address, the position of the virtual address in the page is the same position as the physical address in the page frame. So you calculate the distance, or you calculate the position of the address that you want to map in the page and apply the same position, like the same offset, in the page frame. This is how you map virtual addresses to physical addresses using a mapping given in this kind of diagram. Okay? And this is what the MMU does, right? So the MMU sees we have page 2 for this address. It maps to page frame 6 and transform this address 8,196 to 24,580 and puts the address 24,580 into the bus. The RAM does not know about anything that happens in the MMU. It just sees a request for this address, which it honors, and then fetches the contents of these addresses to the CPU. So this is how it works. Before we go into the details, what happens inside the MMU, because we will take a look at that as well. Let's understand how this mapping works. So there's a task, address translation on ilearn. Let's go over this. Address translation. Oh, we need to make a break. We didn't do a break. Okay. We do a break right away. Here, in this address translation, you have the mapping. It's the same as we have in the lecture. And the goal is to determine the physical address for the virtual address 2000. So everyone figures it out on its own. You have, reciting lecture slides and such, you have 10 minutes to do so. Adding 15 minutes of break, we will talk to each other in 25 minutes again. And once you have a physical address for the virtual address 2000, in this scenario with the mapping that is displayed here, you put the solution into chat, and then I can see how many people are able to do the mapping and how many of you have a correct answer here. Okay, then let's talk in 25 minutes again. Does anyone have a question before? All right, then talk to you in 25 minutes. So how can the MMU do this address translation task within a single clock cycle? And for that, we need to introduce a data structure, which we call the page table. So we hold in main memory a data structure, which is basically a table. A table has rows and a table has columns. And we map the pages which are in virtual memory, so pages are in virtual memory, to physical page frames using that table. This table is in RAM. This table is programmed by the operating system. This table is supported by the translation look-aside buffer to cache frequency translation. And an entry in a table looks like this. So what you see here is a single row, which means this is an entry of the page table. The elephant in the room, the elephant in the page table is the page frame number, because this is what we do. We want to map pages to page frames. So we have a page frame number here at the right half, but there is more information in a page table. For example, we have the present absent bit. This is a single bit in an entry in a page table that indicates whether or not the respective page is in physical memory, so a page frame exists, or it is not, it is stored on disk. Because if we go back a little and see, well, the present absent bit basically indicates to which block on the right side the arrow points to. So for example, the present absent bit on page 10 would be 0, so it's not in physical memory, it points to disk. Whereas for page 9, the present absent bit would be 1, because we have a valid mapping from page 9 to, what is it, page 5. So there the present absent bit would be 1. So in addition to the page frame, we store the present absent bit. We store protection bits. You remember we have these 3 access types: read, write, and execute. This applies for memory, main memory as well. So we learned this in context of files, but this applies for main memory as well. So a user or a process might be not allowed to read some certain page frame, or to write into a certain page frame, or to execute instructions that lie in the content of a page frame. So we have 3 protection bits here as well. Protection bits in our discussion are, I have it here for completeness, such that you know what is in a page table entry. But the next 2 are used in concepts that we discuss later on. The first one is the reference bit. So the reference bit is active. Active means that it holds a value of 1 instead of a 0. When the current instruction accesses the page, so if an instruction is just in the execution in the CPU, the reference bit is 1 in the page table if this current instruction reads or writes to a memory address that is in the page. So active when the current instruction accesses the page. And then we have a modified bit, is active when the page is written to. And this modified bit sticks, so to say. So if a process writes a new value into any location within the page, the modified bit is flipped to active. So it is initialized at 0, and it's active until it is reset, and once a process writes into a location that lies within the page. Okay. So what we do not have here, and this is interesting, I don't know if you noticed, but we want, with a page table, we want to map pages to page frames. So we find the page frame number here, but we do not find the page number in an entry. How so? Because the index is used as the page number. So the position this page table entry lies in the page table is the actual value for the page. So if this is the second entry in the page table, then we would map page 1 to page frame number that is in there. Why 1? because we start counting at 0. So the second entry has an index 1. So page 1 is then mapped to whatever is in this page frame number here. Okay, this diagram looks complex, but if you think about it, it's not as complex as it looks like. This diagram shows the actual mapping. So how can the MMU map virtual addresses to physical addresses in a blazingly fast time? And the concept is as follows. So basically you read this diagram from bottom up. So you start with an incoming virtual address, because in our example, in our running example, we want to map address 8196 to a physical memory location, right? So this is what we want to do. In this scenario, this scales up if you have higher addresses, but in our scenario, what we do is we represent this number 8196 in binary. This is what you see. And in our example, where we have 32K of physical memory and 64K in virtual memory, this is how many? I guess this is 16 bytes. And this would be then 15 bytes in physical memory. Let's count. 1, 2, 3, 4, 5, 6, 9, 11, 12, 13, 14, 15, 16. Yeah, it's 16 bytes. Virtual addresses and 15 bytes because it's one less physical addresses. So in this scenario, what you do with the 16 bytes is you split it up in 4 and 12. The 12 least significant bytes, so these are the 12 bytes that are on the right-hand side, these are not touched at all. So we shelve these 12 bytes and we focus on the 4 bytes that are left over. Because these 4 bytes here in green background, these are used as an index to the page table. So 0010 is binary virtual address 8196 is in fact on page 2. This is how this works in binary. And this is, again, another reason why things are going or things are calculated in binary, because these kind of things work out in binary. So we know 8196 is in page 2 because we take a look at the first 4 bits. Page 2, if we take this, what's in blue background here as page table, page 2, we take a look at index 2. Index 2 is here, and the frame in binary is 110. And we have the present absent bit here as well. So we take this page table entry and we take the page frame, and it's not the whole binary number, it's just the replacement for the first 4 bits. So we replace the 4 bits, so 0010, with what we find in the page table, 110. And this can be done in an instant, right? So it's supported by the translation look-aside buffer. You have this page table in memory. You have a cache in between. So this access is really, really, really fast. So you can make these page table entries, this table lookup inside the CPU with the TLB. So this happens very, very fast. And then you take a look at the present absent bit. If it's 1, this is an indicator for this page frame that you see here is actually, or holds the actual content of the page that we are looking for. So the present absent bit is 1, and we append the content of the frame of the page table to the 12 bits that we shelved before, put this together, which is a 15-bit number. And if we translate this from binary to decimal, this is exactly the 24,508. So the MMU does not do any additions, calculations, and whatnot. It only does bit operations. And this bit operations can be done in electrical circuitry. Then it happens as fast as it can travel through these small copper/silicon wires. So this is close to the speed of sound, how this happens. And this is done in electrical circuitry, taking the first 4 bits of the incoming address, making the table lookup, and putting or replacing the first 4 bytes with the 3 bytes found in the page table, and the mapping is done. So this is how the MMU does it, and this is how these things work in binary. So the address translation process, take the 4 bits, we do a lookup in the page table, we take a look at the present absent bit. If it's 0, we give control back to the operating system and say, well, we have a page fault here. Please, operating system, handle this. But if the present absent bit is 1, we replace the 4 bits with the 3 bits that we find in the page frame, or the page frame number that we find in the page table entry. And then we, this way, we assemble or we compose the physical address. So what happens in case of a page table fault? So control is given back to the operating system. And the operating system knows that the process tried to access a page that is not currently loaded in physical memory. So the task of the operating system is to load the contents of the page that the process was accessing from disk into memory, because the CPU, the control unit of the CPU, can only fetch from main memory. So if the corresponding page frame is on disk, the operating system is tasked to load the content of the page on disk into an empty frame in main memory. And there we can save a little bit of time, because the operating system takes a look at the page table and takes a closer look at the M bit. If the M bit is 0, so the M bit is the modified bit here, it's active if a page is written to. If this is 0, then we know that the content of this page frame did not change. And if it's already stored on disk, then we don't need to write the contents of the frame to the disk, right? And this is a speed up. So the operating system picks a page frame to be replaced. We will see algorithms how to do so. Then we take a look at the M bit. If the page frame that we throw out of the main memory in order to make space for a frame from the disk, we take a look at the M bit. If the M bit is 0, we don't need to write the contents out, because this writing process to disk is very expensive. If we need, or if the M bit is 1, then we need to write the contents of the page frame that is to be replaced to the disk, and then load the contents of the page that was requested into the page frame that was, or the frame that was freed up by this process. And finally, we update the page table entry, like flip the present and absent bit, reset the M bit, and restart the instruction that caused the page fault. Basically, what the operating system does, if a page fault occurs, the operating system needs to make space in the physical memory, load the contents from disk into physical memory, and then restarts the whole process. And the main question is, which page frame should we pick? And this is a very, very crucial question. So if physical memory is full, and a process requires a page that is currently stored on disk, how can we make space in physical memory to load this requested page? And first, let's think about the optimal placement. The optimal page replacement would look like, well, we know So we need to reduce the number of times we need to do this operation. We want to avoid accessing the hard drive as much as possible. So an optimal page replacement would be then a page, or a page frame to be more precise. We want to remove the page frame where the likelihood of loading it in again is the smallest as possible. So we want to select the page frame that we throw out based on the information on how long it takes to swap this page frame in again. And we just take the page frame that needs to be loaded in or along, we need to maximize the time we need to load it in again. And the idea is to label each page with the count of instructions, with the number of instructions that will be executed before that page is referenced again, before we need to load it in again. So for example, if we have 2 pages, and one page will not be used for 8 million instructions, and one page will not be used for 6 million instructions, we will throw out the page that is not used for 8 million instructions, because over time, we reduce the number of times we need to load something from disk or write something to disk. And this is the optimal, right? Maximizing the time it requires to load the page frame that you throw out, to load it in again. The thing is, we cannot peek into the future. So the count of upcoming instructions until next reference is something that we can rarely predict, because it depends on so many factors, and all approximations are a little bit off. So this algorithm is impractical. We cannot predict the next reference on each page during a page fault. So we need to do the next best thing. The next best thing is an algorithm that is based on the following observation. So researchers took a thorough look at this problem and say, well, how can we approximate the optimal algorithm at best? And what they did is they took a look at the frequency of the page access. And they found out that pages that were accessed frequently in the past are accessed frequently in the future as well. So the frequency of page access is unlikely to change over time. I mean, it happens time to time, but over all the millions and billions of page accesses, the frequency of page accesses stays somehow constant over time. This means that pages that are untouched for a long period of time are likely to be untouched for another long period of time as well. And what we describe here, because the pages that are untouched, these are the ones that we want to throw out in order to make space in physical memory if memory is overloaded and you want to load a page frame from disk. So the untouched pages, these are the ones that are interesting for us. And as it turns out, if we choose this is the least recently used page. This is a good candidate for the optimal, for a replacement for the optimal algorithm. So we cannot put the optimal algorithm into practice because we cannot predict the future. But a good approximation is choosing the least recently used page frame. And now we are at the algorithm least recently used, LRU. I guess the most important replacement algorithm that we have. It applies to page replacement in context of main memory. It also applies on caches, because caches have the same problem, right? If the cache is full, how do we select a good candidate for throwing an entry out of the cache in order to make space. And there, LRU is also an algorithm that is commonly used. And we use it for page replacement in our virtual memory context. So least recently used LRU replaces the least recently accessed page frame. The procedure is as follows. So when we start initially, we have an empty memory, right? So we begin with an empty list of page frames in memory. And then we decide two scenarios. Is it a page hit or is it a page miss? If a page that we want to load into memory, and this also applies for the initial loading of a program. So let's assume the whole address space is empty and we start to load a program. Then the memory controller, or the part of the hardware-software combination that does memory management, it's a mix of operating system and MMU. So if a reference page is in a frame, then we have a page hit, and then we change the order, because now if a page is referenced, it's the most recently used frame, right? And we keep a list of frames and order the list based on is it most or least frequently used. So if we reference a page, we move it to the front of the list. If a reference page is not in a frame, then we first check if there is an empty frame somewhere in memory. If so, we load the page into the frame. If no empty frame exists, we need to figure out the page that we want to throw out in order to load the new page that is not in a frame. And for that, we take the back of our list, because the back of our list is least recently used. So whenever we move frames to the front of the list when there is a page hit, we maintain an order in the list where the back of the list is the least recently used page. Let's see this in an example. So in this example, we have 5 pages and we have 3 page frames. So these are the page frames, and we have 5 pages. And these pages are page 1, 2, 3, 4, and 5, right? So make this simple. And the sequence of page accesses should be: first we access page 1, then we access page 2, 3, 2, 1, 5, 2, 3. So you read this from left to right, where these are the incoming pages. So you access these pages in sequence. So basically accessing memory locations that are part of this particular page. And our physical memory is divided into our page frames, and we need to fit pages into page frames. So let's do it according to the algorithm previously shown. So initially we start with an empty mem, right? And we start to load the program. So we load page 1. Page 1 is not in memory, but we have free space in our page frames. So we locate it here, but it is a page miss. Then we do the same with 2, it's a page miss, and we do the same with page 3, it's a page miss. So after 1, 2, 3, things get interesting, because after 3, we reference 2 again. 2 is in fact loaded into physical memory, because we have a page frame. It's the middle page frame here where page 2 is located in. And according to the LRU order, we move it to the first list. So in order to demonstrate the LRU order, I say, well, when a page is on top, it has a higher order, or so this would be then the list, and this the first one would be the front of it. So 2 moves to the first position in the LRU list. Then we reference 1. 1 is also loaded in a page frame, and we move according to the LRU order the page 1 to the front of the list. So the contents of the LRU list is 1, 2, 3. So this is the current order. Then we reference 5. 5 is not in there, right? So this is a page miss. And in order to select the page that we throw out, we simply take this one, page 3, because this is the least recently used page. We throw out page 3. We shift 1 and 2 like one place to the right, and the load 5 in. 5 is the most recently used page, so it's at the front of the list. So whenever we load something into a page frame, it is the front of the list. Then we reference 2. 2 is a page hit because we have it here. So 2 moves to the front in our list. The rest is 5, 1. And then here we have a page miss again. Page miss means that we replace the least recently used. In our case, it's the back of the list. It's 1. So we remove 1. 3 is the front of the list. So the LRU order is 3, 2, 5. And you do this over time. This is how least recently used. The problem with LRU is the following. Page accesses that represent the second level of your game, then this second level pages have high count values. And once you proceed to level 3, you do not need the pages of level 2 anymore. But these, because level 2 is a big level, these have high counters, and you have a fluctuation. You have swapping ins and swapping outs in a high frequency, because level 3 is smaller, and the level 3 pages do not get as high the values as the pages of level 2. And this is a drawback. So once pages hit a high level, they basically stay in memory for all eternity. And you do not want that. You have the same in system boot up. When you boot a system, load an operating system, then the pages that are used for booting the system are in, and you do not get it out anymore. So you need a slight modification of not frequently used. This is what we call aging. We want the counters to degrade over time, right? So and this is the best LRU approximation. The best LRU approximation that we have, the aging modification of not frequently used. And this works also in binary, and it shifts the counter one position to the right before appending the R bit to the left. So the R bit, we have it here. So this is the counter, right? So how many bits are these? It's 8-bit, it's a byte. So the counter is a byte, and we have the R bit. We shift in every time unit. So this can be a number of cycles or timer ticks. We shift this binary number by 1 position to the right, and then we add the value of the reference bit to the left. In this example, so if we start at T0, we have a 8-bit number, and 10007 times 0 is, what is this? 265? I guess it's 265. 2 to the power of 8, 265. Let me double check. 2 to the power, let's double check in Python. 2 to the power of 8, 10, cannot be. the power of 8 cannot be 10. Because in Python, the power operator is this one. Yes. Thank you, Raman. The power operator in Python is double star. The other one is, I guess, some binary operation. 2 to the power of 8 is 256. Okay. So this is binary 256. And whenever we bit shift a binary number by 1 position to the right, this would be 2 to the power of 7. And you see it here. It halves the number. So a bit shift to the right is multiplied by a half. So this would be 128. And here you see the effect by doing the bit shift and adding the reference bit to the right. Because the reference bit, if it's 0 all the time, this means that there is no access to the page. And after cycle, we multiply this counter by a half and degrade the number over time. But if the reference bit is 1, we want the counter to be high numbers, right? Because if we reference a page, we want to keep the pages that are referenced in a high frequency. We want these to be in memory, right? And with this bit operation, we achieve exactly this effect. If the reference bit is 0 all the time, we degrade the counter. So at every step we halve it. If the reference bits is most likely 1, the counter is kept high. And in fact, I guess there is a mistake there. This one should be 1 position to the right. So if please note that down, that this is a mistake in the slides. This number should in fact be 1 0 and another 0 1, because we have 2 zeros here. And then a 1. So this one here, the inner 1, it should be positioned 1 position to the right. And this applies for this and for this entry as well. So I will update the page, I guess today in the afternoon. But if you have like a version downloaded, there's a mistake in there. Okay, so the story of page replacement is optimal algorithm, we cannot predict the future. LRU, the closest thing to the optimal, but too slow. NFU would be a good candidate, but it has the aging problem. The aging variant of NFU, as we see it here, this is how we approximate LRU the best. So the story as up to now is we can approximate LRU pretty quickly with the method that we just saw. So let's see what the Linux kernel does in page replacement. This is an active field of research, and it has in fact changed. So the page replacement algorithm was changed in kernel 6.1. I guess you have newer kernels because 6.1 was released a couple of months ago. So what kernel do I use? uname.a. I use a 6.5 kernel, and I guess I want to highlight how page replacement worked until 6.1, and I also give some sneak peek how page replacement works after kernel 6.1. So the idea is still LRU. So LRU is the way to go. But the kernel wants to address a single scenario. But before we talk about the scenario, let's first see how page replacement works in the Linux kernel prior to 6.1. We have 2 lists, not a single LRU list. We have 2 lists, and we call them the active list and the inactive list. And you see the gist here. On the active list, we want to have pages that come from active processes, active being that these are processes that the user interacts with, such as my slideshow presentation or my streaming software or my browser. These are active processes. We want the pages of the active processes on the active list and what's not on an active process on the inactive list. And when the inactive list is full, well, we write the page to the disk. So pages that have been recently accessed are kept on the active list. Both lists work according to the least recently used principle, right? So pages that have recently been accessed are kept on the active list, and pages that fall off or are replaced from the active list are joining the inactive list. So this is like a second chance, so to say. If a page is replaced from the active list, it joins the inactive list, but this list is still in memory. If an inactive page is accessed, so a page that resides on the inactive list, it's promoted. So whenever an inactive page is accessed, it's promoted to the active list, because access meaning that an active process has accessed this page. But if pages if there needs to be some space on the inactive list, pages are removed only from the inactive list. Pages are never removed from the active list. And when a new page joins, it always is joining the inactive list. So what you, like conceptually, what you have here, basically a second chance system, where you say, well, if you're an active process and you lose, or the frequency of access goes down, you fall down to the inactive list first. And then if a page is not accessed again, it falls off the inactive page. So this inactive level is basically a second chance that a page has. And why should we do this? So why don't we use just a long LRU list, right? Because physical memory is limited. And we have the option of one long LRU list or two lists, active and inactive, that have half the size, because physical memory is limited. So why do we do this? It's efficient in situations where we have sequential access and we need the information of this sequential access just only one time. So this is a scenario where you load a file into memory, but you never use it again. So you want to read a file one time, but not a second, not a third time. And by dividing the pages up in an active and inactive list, and importance, newly allocated pages first join the inactive list, this means that you have this file only in the inactive list because you access it once, and you still have processes on the active list which reference pages of active processes, right? So in order to get to the active list, you need at least to have two references. And if you read a file, you only get one reference, right? And this is basically a concept where you say when you want to read files, you need them in memory, but you want to throw them out pretty fast. And with this active-inactive list kind of concept, you achieve exactly. So this is how page replacement works in a Linux kernel. Two LRU lists, active, inactive, with this second chance kind of system, with demotions and promotion. So Yuzhao at Google in Palo Alto in the Silicon Valley proposed an idea in 2021. I have the link below. And this is what happens in the Linux kernel after 6.1. Basically, it's the same idea. And the idea is to have more than two lists. So the kernel before divided the physical memory into two halves. We have inactive and we have active. And the idea of Yu Zhao at Google was to create more of these lists. And we call them generations. So instead of 2 lists, we maintain 20, 25 lists. This means we have more lists to manage, but these lists are also smaller in size, right? Because if we have physical memory, the size of the list is then smaller because we are hard limited by physical memory. And the same concept applies. You only remove pages from the last list. Like in the example before, this would be the inactive list. And these lists are smaller. And if we only remove from the last list, which is smaller, we can perform this replacement pretty faster. So the page replacement takes longer, the longer the list is. If the list is smaller, well, the page replacement does not take as long time, right? So it makes a difference if you search for a page in a 2 billion list instead of a 2000 list, right? So this is a huge difference. So by adding more lists, we reduce the size of the list that we scan in page replacement. And there's another effect. So the same, it is promoted to the next list above. And if we do page replacement, it can happen that a page from one level is dropped to the next lower level. So if we have like 20 levels, pages are promoted to upper levels and are demoted to lower levels. And if we do it according to the LRU principle, this means that we have highly frequented pages at the top levels, and the pages that have a lower frequency in access are at the lower levels. And with multiple of these lists, what you get is like a frequency spectrum of pages. So highest frequency are in the oldest generations, which are on the top, and generations that have low access frequency are in the youngest generations. Generations are small in size, we talked about that. And only the youngest generation is scanned, which is the efficiency gain. And this was merged into kernel 6.1. And I don't know what the release date of 6.1 was, but it was in the last year. Kernel 6.1 release date. So this was introduced in December 2022. So roughly a year ago. Please take a note that this is an excursus, meaning that this is not relevant for the exam. What's relevant for the exam is page replacement in the Linux kernel. So you would need to explain what's the matter with these active and inactive lists, the extension of that, just like a peek. What happens in research in page replacement algorithms, and this is an active field of research where people may contribute. There's an assignment. We do not talk about memory segments. This is a small, just a very small part, which we address the next time. Let's take a look page replacement on iLearn real quick. So the next task would be page replacement, which is a bigger task. It is a scenario where we have 8 pages and 4 page frames, the same way as we have seen it before on the slides. We assume that physical memory is empty and we have a sequence of page access. So 0, 1, 7, 2, and so on and so forth. And you should do a sketch of the contents of physical memory after each incoming page. one time in first in, first out, one time in least recently used, and you need to determine how many page faults will occur. So this is basically, if we go back, this is something like this. This is our sequence of page accesses. We have 4 page frames in the task, 3 page frames here, and the number of pages here is 5, and in the example 8. But you're supposed to like sketch an illustration of the physical memory after each page access, like similar that we saw it here. And as time is progressing, I want you to do this as homework, both. So think about it. Try to figure out a sketch for that. This is also, this is an old exam question, so this is highly relevant for the question. Please train this. And we start with discussing or reciting these page replacement algorithms next week. Are there any questions? No questions? Then let's conclude. Thank you very much for your attention, and talk to you next time in blocks 2 and 3. So we follow the regular schedule in next week. So have a nice time and see you soon. Bye-bye.